Okay, so today we start our last topic, and to do this, we're going to be using these notes as our book. We'll be stepping outside of the book. Okay, so our topic today then is sequences. I'll explain what sequences are, and limits, how limits apply to sequences. Okay, so to understand this, let's consider an example. Okay, so our example is this. Okay, so a doctor orders you to take 16 milligrams of a drug You'll do this every 12 hours for 10 days. Okay. All right, so we take, this is how we're prescribed. We're supposed to take 16 milligrams of this drug every 10 hours for, or every 12 hours for 10 days. That means we're going to have 20 doses to take in total. Now, we're going to assume here, because our body will process it, so we will assume that our liver and kidneys can process or remove 25% of the drug from our bloodstream. In the same amount of time, in 12 hours. So here's our prescription. Our kidneys are going to be removing some every 12 hours. And now we'll ask ourselves, so what happens to the drug level in our bodies over the 10 days? So let's see what happens with that. Okay. So what we'll do is we're going to create something we call a model. We're going to mathematically model what is happening to our bodies. Okay. We're going to need some notation here. So we're going to have 20 different doses. So let's let a dose be 1, or D, and our first dose will be D1. Our second dose will be D2, so this is our first day. Then on the second day, we take our third dose and our fourth dose, etc., 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 etc. Okay, so these are doses. So our first dose, which is the initial one, there is none of the drug in our system until we take it. So now we have 16 milligrams. Now it's 12 hours later. Okay, so I'm going to take another pill, which puts 16 milligrams back into my body. Okay, but I still have some from the first dose. That is, if my liver and kidneys can remove 25% of the drug, that means that 75% of the first dose is still in my system. All right, well, we can figure out what that is. That's 16 from the original, or from our new dose, and then 75% of what we had prior, which was 16. Which is 16 plus 12, so now there's 28 milligrams of the drug in my body. Now it's the second day, so I'll take again another 16 milligrams from the pill, but we still have some remaining. That is, 75% remains of what there was yesterday. And when you crunch these numbers, we find then that means at the third dose, I have 37 milligrams in my body. All right, and so this is going to continue. So let me show you. So what that means that in general then, any dose I take is 16 from the pill plus 75% of the prior dose. Okay, so a dose of any time n is 16 plus 75% of the prior, so d sub n minus 1. Okay, so this is some notation. Right? So here's what we saw. The first dose was 16, and then 28, 37, and then it begins to keep going, and we're at 43 to 48, 52, 55, 57, and while these numbers are increasing, we can see that they are slowing down. Okay? So if we were to actually plot these, okay, so let's plot the dose, so our first dose, and then in milligrams would be 16. So that's our first point that we could plot. This would be the point n is our first dose, so that's our first dose, and there was 16. On the second dose, there's 28. On the third dose, there's 37. Okay. On the fourth dose, there's 43.75, etc., etc., etc. So that's how we plot each of these points. And as we're doing it, we can see that they seem to be bounded. And specifically, we talk about this as being bounded, that is, there is a bound, and it's bounded from above. And specifically what number we're looking at here, where we can see that it's approaching 64. Okay, that's what this is supposed to be telling us. And we can think then as, what would happen if we continue past 20 doses? Well, it appears then, because of this boundedness of the graph, how the graph is leveling out, it appears that even as n increases, that is, the number of doses increases, it's that this sequence will be approaching and bounded by 64. So why we bring this up is that this is an example of a sequence with a limit. Okay. Now notice I didn't connect these dots because these are actually what we call discrete. I don't take a 1.5 dose. I take my first dose and then I take my second. Okay, so these are not connected. But these numbers appear, if we graph them, to be bounded. Okay. So a sequence then is just a list of numbers. Okay, so for example, here, D1, D3, all of these through D20. Okay. This is a finite sequence. Then they have a corresponding part with the 16, 28, 37, etc., etc., etc. This is a finite sequence. That is, it ends. Now, notice I have these already written out, but one way I could do it, because I don't particularly want to write every single one in the sequence, is I could write 16, and then 28, and then 37, and then I could put in these ellipses indicating that there are more, and then that the last one would be 63.8. Okay. So a finite sequence has a ending point. But we wouldn't have to do that if we wanted to dose forever. Okay. One way I could write that then is I could write that as this. I could say, well, I have my first dose, my second dose, my third dose, etc., etc., etc. And then I would like to just indicate that there is some form that these doses will be taking, and then I'll put some more ellipses to indicate that this is an infinite sequence. Now, I don't know where exactly this is, each one corresponds to, but I know that the first dose was 16, and I know that this is 28, and I know this is 37, we had another one at 43.75. I could also indicate an infinite sequence this way by putting the ellipses in. And what we could write then is we could say then that there is a limit for the nth term, or the nth dose. I don't know exactly what it's going to be, but if I continue dosing forever, that is, if I let n go to infinity, the limit of this sequence has to be 64 because it's bounded above. And we read this, the limit as n goes to infinity of what? Not of a function anymore, but of our sequence d sub n. Well, we know that limit is 64. Okay, so let's just then define this a little bit more clearly then. A sequence is an ordered list. Okay, that is ordered matters, okay, of numbers. In its simplest form, this is what a sequence is. Okay. Now, there is some notation for this. Okay. We could list it as a set. Okay. And we know that each of these list of numbers, we'll just do it in general, we'll call the first one A. And to note that it's the first in the sequence, we put sub 1. The second would be A sub 2. The third would be A sub 3, etc. There would be some nth term, which we'll denote as A sub n. Okay. And let's make this one infinite. Okay. And then we could close the set notation. Or what we can do is we can just, instead of writing all that out, we can just use our set notation and write A sub n. Okay. And these are both notations for a sequence. Okay. Now, this list can be infinite or finite. It doesn't matter. Okay. We call the individual numbers in the sequence the terms. Okay, so these are terms. A sub 1, A sub 2, A sub 3, and this is known as the nth term. So first term, second term, third term, nth term. Now what we can do is that we can think of each sequence, we can think of it as a function. So this is just the definition that we wrote down here. We can think of it as a function who, okay, so a sequence is a function where the inputs, okay, now remember the inputs, we think about this as domain. Okay. We also think about this as the independent variable. Okay. This is what other words we've used for this. So the input into our sequence is the set of natural numbers. Now I know it's been a long time since we talked about at the beginning of the semester what a natural number is, but remember a natural number, we'll call it n, starts at 1, 2, 3, 4, etc. It's the set of positive integers. It does not include 0. And we would see that here. N equals 1, it's the first term, it's the second term, it's the third term, it's the fourth term, etc., etc. So if our domain, if we made a mapping, the number 1 maps to the range, and what is the range in this case? It's the first term. So 2 would map to the second term. 3 maps to the third term, etc., etc., etc. So that for any number, natural number n we pick, it will map to the nth term. Alright, so that's a basic idea and understanding of what a sequence is. So now we're going to look at several examples and look at their behavior and some vocabulary. Okay. So for example, now, let's do this one. So here we've defined what our nth term will look like. Okay. So here's another way to list a sequence. And so, all right, if it's a function that deals with a set of natural numbers, then the first in our sequence would be f of 1. And I can substitute 1 in for any place I see the n. Okay, so f of 1 is 1 over 1 plus 1, which is 1 over 2. So this is our first term. Let's find the first 5. Okay, so I need to find f of 2. So in f of 2, now I put in 2 over 2 plus 1, and then simplifying that, we get 2 over 3. Okay, this is our second term. And we continue, f of 3 becomes 3 over 3 plus 1, which is 3 over 4. This is the third term. F of 4 would be our fourth term. So we get 4 over 4 plus 1, which is 4/5. This is the fourth. And f of 5 will be the fifth term. So 5 over 5 plus 1, which is 5/6. And I can continue on in this manner, and I can, because I know what the nth term looks like, I can determine what any term looks like. So, for example, the 100th term, f of 100, this would be the 100th term. Well, we just do it the same way because we know what the nth term looks like. That's 100 over 100 plus 1, which is 100 over 101. This is the 100th term. We could find the 1000th, no problem, same way. Now we just put in 1,000. And what we get then is 1,000 over 1,001, and this is the 1,000th term. So that's the benefit of knowing what our sequence is in terms of n. Now, we could write that in a different way. We could write this using our sequence notation. Okay. That is, the sequence that f of n generates is the set of 1/2, 2/3, 3/4, 4/5, etc., etc., etc. We found the 100th term. There's more in between. We found the 1,000th term. So remember what these are. This is the first term, a sub n. This is the second, a sub 2. This is the third term, a sub 3. This is a sub 4. This is a sub 100. And this one is a sub 1,000. Okay, these are the terms. Alright, another way we could define it, instead of saying f of n, another way we could list it, here's a different example. We could say a sub n is equal to, so just automatically writing the nth term, is equal to, now in this case, let's say negative 1 to the n over 2 to the n. So let's find the first 5 terms. Right. So a sub 1 is negative 1. We're going to raise that to the nth power. Okay. But in this case, remember n is equal to 1, so this is to the first power, and this is to the first power. So negative 1 to the first is negative 1 over 2. So the first term, a sub 1, is negative 1/2. Now a sub 2 will take negative 1 to the n power, and again 2 to the n power, but in this case n is 2. Now when we simplify this, negative 1 squared is positive 1, and 2 squared is 4. So the second term is a sub 4, or is 1/4. A sub 2 is 1/4. A sub 3, and we'll just continue in this manner, negative 1 to the n over 2 to the n, and in this case, n is 3. So when we simplify this, we get negative 1 cubed, which is negative 1, over 2 cubed, which is 8. So a sub 3 is negative 1/8. A sub 4, again, negative 1 to the n over 2 to the n. And now n is equal to 4. And negative 1 to the 4th is positive 1, and 2 to the 4th, 8 times 2 is 16. This is a to the 4th. A to the 5th or a sub 5, the 5th term, is negative 1 to the 5th over 2 to the 5th. Negative 1 to the 5th is negative 1 over 2 to the 5th, which is 32. These are the first 5 terms. And again, we could find any other terms that we'd like. A sub 100 will be negative 1 to the 100th power over 2 to the 100th power. Well, I don't know what 2 to the 100th power is, so we can just simply leave it like that. But I do know that negative 1 to the 100th power, since this is even, is positive 1. Okay. Again, we could do the same thing for 1,000, negative 1, 2 to the 1,000. Well, again, we'll just leave 2 to the 1,000 as 2 to the 1,000. Okay. But 1,000 is even, so I know that this has to be positive 1. And so we could list these. Another way we could write this is that the sequence, okay, written like this, we could list it out in terms. It's negative 1/2, then positive 1/4, then negative 1/8, then positive 1/16, then negative 1/32, etc., etc., etc. Okay. So notice what's happening here is that the signs are changing, and so this is known as an alternating sequence. Okay, it changes signs. Negative, positive, negative, positive, negative, positive. Let's do a few more. Okay, what if, for example, we had f of n is 2n minus 1. Right. So what happens, this is a very popular notation for us, and I'll show you why this combination is 2n minus 1. Alright, so let's find the first 5 terms. So f of 1 is 2 times 1 minus 1, 2 minus 1, which is 1. F of 2. 2 times 2 minus 1 is equal to 4 minus 1, which is 3. F of 3 is equal to 2 times 3 minus 1, which is 6 minus 1, which is 5. And I hope we can see what's happening here. F of 4 then, well, that's going to be 8 minus 1, which is equal to 7. F of 5, and I hope we can see the pattern here, 1, 3, 5, 7. F of 5 is 9. So this is the set of odd numbers. Okay, we could rewrite the sequence here. We could write it as f of n, and then we could list it. 1, 3, 5, 7, 9, etc., etc., etc. Okay, so a couple different ways for us to write this. Okay, so this is the sequence. Okay. Now let's find. Here's another example. What if a sub n is equal to negative 1 to the n minus 1? Okay, so this is also going to be important for us. Let's see what happens when we generate this. Okay, so a sub 1, or a of 1, which is the first term, negative 1 to the 1 minus 1, which is negative 1 to the 0. And remember, anything to the 0 power is simply positive 1. Now, for the second one, the second term, negative 1 to the 2 minus 1 becomes negative 1 raised to the first power, which is negative 1. A sub 3, negative 1 to the 3 minus 1 is equal to negative 1 squared, which is positive 1. A sub 4 is equal to negative 1 to the 4 minus 1, which is negative 1 cubed, which is negative 1. And I hope we can see what's happening here. This is also an alternating sequence, and a sub 5 should be positive 1, which if we check it out, it will work. Negative 1 to the 5 minus 1, which is negative 1 to the 4th power. And then we could write out the sequence, a of n. Well, we can write it out. It's just 1, negative 1, 1, negative 1, 1, etc., etc., etc. So again, this is alternating. So an alternating sequence happens when the signs alternate. But let's write down a definition of what that would be, a more formal definition than that. Okay, so you will need to know these. Alternating. Okay, a sequence is described as alternating if the signs alternate throughout the sequence. Okay? So it just can't be a couple of them that alternate. They have to all alternate. So another way for us to say this is a sequence a sub n is alternating if the nth term is equal to the negative of the one after it. for all n. Okay. So, for example, we showed you a few of these. The negative 1/2, 1/4, negative 1/8, positive 1/16, etc., etc., etc. Or it can bounce in between negative ones, positive ones, anything like this. Okay. So the signs are changing. Okay. We also have something called strictly increasing. So when a sequence is strictly increasing, the sequence a sub n will have a certain characteristics. A sub n is strictly increasing if, okay, so here we'll take our nth term, okay, and then we'll look at the term right after the nth term, so a sub n plus 1, okay, so the nth term and the one right after it. If it's going to be increasing, well then the previous term has to be less than the one that it follows, or less than the one, that follows it. Okay. So, for example, we had a couple in here. Clearly, the odd numbers 1, 3, 5, 7, 9. This is strictly increasing. 7 is less than 9, 5 is less than 7, etc. Also, 1/2, 2/3, 3/4, and 4/5. Okay. This is also strictly increasing. 4/5 is greater than 3/4. 3/4 is greater than 2/3. And then there's the opposite one of strictly, also for strictly decreasing. Strictly decreasing. Then it's got to go the other way. Then we want, when you compare any two terms, the nth and the one after it, then if it's decreasing, then a sub n has to be bigger than the one that comes after it. Okay? For all n. And let's officially define what boundedness is. A sequence, remember we'll call it like this, a sub n, is bounded above if there is some value that is greater than or equal, let's include that, to all terms in the sequence. Okay. Well, what should we call this? A value. Okay, so in other words, let's call this a value. That means there is a value. Let's call it m. And such that what happens? Well, when you take any term in the sequence, a sub n, we'll just call it the nth term, all of those terms in the sequence have to be less than or equal to this value for all n. And we could be bounded below And now what happens is we still have this value m, but now when you compare a sub n and m, okay, the terms in the sequence will be greater than or equal to this value for all n. Okay, so a few of these, let's look back at these. So our example, we had 1/2, 2/3, 3/4, 4/5. Okay. This example is it is bounded. Okay, this is bounded above, because for any term in this sequence, it has to be less than or equal to 1. 4/5, the next one's 5/6, 6/7, 7/8. All of these are going to be lower than 1, so it's a bounded from above. And we can also talk about it as being bounded from below, because this is the smallest number, because this is strictly increasing, then any term in this sequence has to be greater than or equal to 1/2. So it is also bounded below. Let's look at the alternating example. -1/2, +1/4, -1/8, +1/16, etc., etc., etc. So we ask ourselves, is this bounded from above? That is, if I compare all of these terms in here, are they all less than or equal to some number? So let's think about this in terms if everything was positive. Okay, so if we had +1/2 and then +1/4 and then +1/8 and +1/2, etc., etc., then the largest number would be 1/2. Or is it that it's bounded below? Okay, if they were all negative, then I'd have -1/2, -1/4, -1/8, -1/16, and so these are becoming less and less negative. So the very largest number would be -1/2. If they were all negative, they would be continuing towards 0. Okay? So the lowest number here is -1/2. So even with the alternating, because these numbers are getting smaller and smaller and smaller, the next one's 1/32, etc., etc., etc. So now is it bounded by above? Well, what is the most positive number that we can have? And that has to be the 1/4. Okay? Because all of these numbers are getting smaller. The next positive number is 1/16, which is smaller than 1/4. So this is why we are bounded above and below. What about the set of the odd numbers? Are they bounded? 1, 3, 5, 7, 9. This sequence that we generated. Okay. Is it bounded above? Absolutely not. There is no value because this is strictly increasing. It's going to increase. So it is not bounded above. Okay. It is, however, bounded from below, the very smallest number that we have. Every term in this sequence is going to be greater than or equal to the first term, which is 1. Now we have this tricky sequence. We have 1, negative 1, 1, negative 1, 1, negative 1. And so is it bounded above? Is it bounded below? So if a sub n, when we compare them, if it's bounded above, then every term has to be less than or equal to some number. In this case, we only have 1 and negative 1 to deal with, so yes, it's bounded from above. Every term is either less than or equal to positive 1. And similarly, it's bounded below because every term is greater than or equal to negative 1. Okay, so what this is getting to, that's some description about various types of sequences and vocabulary associated with them. Now, we are often interested in the long run behavior of a sequence. Okay. And so in this case, we'll be talking about a limit. Okay. So as n increases, how does the sequence behave? Is the sequence approaching some finite value or not? Okay, so this is what we're going to be looking at. All right, now another word for this long run behavior and another word for limit as it applies to sequences. Definition. A sequence, we'll just call it A sub n. I could call it anything, B sub n, C sub n, it doesn't matter. Okay, is convergent. Okay, so this is our word. Is convergent, that it converges if the terms of the sequence approach a finite value. Then we say the limit exists. And write. Alright, so the limit existing for a sequence will mean that the sequence is convergent, and we can write then that the limit as n goes to infinity, that means as n increases, of our sequence A sub n will be equal to this finite value L. So the finite value we're going to call L. Okay. And if this doesn't happen, so if not, then we say the sequence is divergent. So convergent and divergent. So let's see if we can actually determine some of these. Running out of paper. Okay. Alright, so okay, so we're going to do this by inspection at the moment, and then we will determine something else. A more rigorous way to do that. Okay, so let's look again at our sequence that we had. F of n was equal to n over n plus 1. We saw when we generated the sequence that that was equal to 1/2, 2/3, 3/4, 4/5, etc., etc., etc. And we determined that this was bounded by 1. Okay? So we can see that these terms are getting closer and closer and closer to 1. And it will always be less than 1, okay, because the numerator will always be smaller than the denominator. Thus, this is a convergent sequence, and so we can write the limit as n goes to infinity of f of n. Or we could write it explicitly. We could write the limit as n goes to infinity of not f of n, but we could just say n over n plus 1 is equal to this L, our limit, which is 1. Okay. So then let's look at this sequence. A sub n, this alternating one, negative 1 to the n over 2 to the n, which we said was, when we generated this, was equal to negative 1/2, positive 1/4, negative 1/8, positive 1/16, negative 1/32. Okay, let's see if there is some type of behavior, a limiting behavior. Okay, so let's graph this. Now remember, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. Okay. So if I want to graph this, okay, we put our natural numbers down here. So this is going to represent the first term, this will represent the second, the third, the fourth, the fifth term, etc. So let's see if there's any sort of behavior here. And we said it was bounded above by the number 1 and below by negative 1. Well, we actually said it was a little bit. It was below by negative 1/2 and above by 1/4. So let's see why that is. Okay, so for 1, I need to plot the point negative 1/2. For the second term, a sub 2, I need positive 1/4, which is approximately here. For the third term, I need negative 1/8, so that's less and less negative, which would be approximately there. For 4, I need 1/16. We're getting very, very, very close. I hope we can see what's happening here. Okay. Now at 5, we have negative 1/32. So these are jumping up and down between positive and negative, but they seem to be zeroing in on the number 0. Okay. So by inspection, what we can say then is that the limit of this function does exist, or of this sequence, which is a function. The limit as n goes to infinity of a sub n, or I could write the limit as n goes to infinity of negative 1 to the n over 2 to the n. Well, it's 0. All right, let's see. We have another one here. Let's do this one. We also looked at f of n equal to 2n minus 1. Remember, this is the sequence that generated the odd numbers, 1, 3, 5, 7, 9. We said this was strictly increasing, and that the terms of this sequence increase without bound. Okay, there is no bound, so there was no boundedness to this, and so this is a divergent sequence because the terms do not approach a single value. So one thing we can write is that the limit as n goes to infinity of this function is equal to infinity. And remember, this is just notation where we know it's a divergent series, or sequence, I'm sorry. Now what about this alternating series? Does this have does this have a limit? Okay. So what was that? That was a of n, which is equal to the set of 1, negative 1, 1, negative 1, etc., etc., etc. Now, we did say that this sequence was bounded from above and bounded from below. However, does the limit of this exist? That is, as n increases, do the terms approach a single value? So this is the sequence where, okay, so this is a sub 1, a sub 2, a sub 3, a sub 4. Okay. If we were to graph it, let's look and see. 1, 2, 3, 4. Here's 1, here's negative 1. Well, the first term is positive 1, the second term is negative 1. First term is positive 1, negative 1, etc. So what we see then is if we were to keep graphing this, as n goes to infinity, this graph does not actually approach a value, it stays here. So in this case, it does not increase without bound. So it's not that the limit is infinite, and there is no number. Okay, so in this case, we will just say then that the limit as n goes to infinity of a sub n, well, we'll just say that that does not exist. And so, again, this is divergent. All right, and then there's some tricky ones. Let's say I have a sequence b sub n, which is just equal to 3. So what sequence is that? Well, the sequence that generates is simply just 3 repeating. So will the limit exist for this function? Sure, it's the constant function. Then the limit, or not constant, but function, but a sequence. And so the limit as n goes to infinity of b sub n is just equal to 3. Okay. So this is both bounded above by 3, it's bounded below by 3. The limit exists here, and therefore it is a convergent sequence. Okay, let's try some more things here then. Now that we can identify them. Alright, so let's, now that we kind of have an idea about what the limit of the sequence is, let's try and build to a more formal definition, okay? Okay, so we have a more formal definition. So far we've determined the limits by inspection, but what does it mean mathematically when we talk about the limit as n goes to infinity of a sequence being equal to L? What are we saying? Okay. So again, let's go back to our example where a sub n was defined to be n over n plus 1. Sometimes you'll see a colon in front of this, and this just means that it's defined to be. Okay. And we already said that the limit as n goes to infinity of a sub n, this one, was equal to 1. Alright, so that means as n increases, this function will be, this sequence, which is a function, will be approaching 1. But at what point will the terms terms of the sequence, when will they be within 0.002, which is 1 over 500. Okay, so when will they be within this this range of the limit which is L is equal to 1? Okay. So let's see if we can figure that out. So remember what the terms of our sequence look like. Okay, when we generate this thing, we get 1/2, 2/3, 3/4, 4/5, etc., etc., etc. Now, these terms are increasing, and they're getting closer to 1. So let's see what we get. Like, if we let n equal 1,000, then the 1,000th term is 1,000 over 1,001, and this is really, really close. Okay. To 1, it's 0.999 repeating, or 199. Okay. If we go to 10,000, then the 10,000th term is 10,000 over 10,001, and this is 9999. Okay, so we're getting really, really close. How far away are we? Well, here the limit is 1, and if I subtract off the 1,000 over 1,001, okay, well, this is 1,001 with a common denominator minus 1,000, that is 1 over 1,001, and this is less than 1 over 500. How do I know that? I know that because the larger the denominator, the smaller the fraction. Okay. So this is what we were looking to be within. So clearly at n equals 1,000, we're within 1 over 500 of the limit. And the same thing goes here. The 10,000 over 10,001, getting the common denominator would leave us with 1 over 10,001. And again, that's less than 1 over 500, which is what we were looking for, to be within that. Okay. So clearly we're there. All right, but what is the first term? First term, that is within 1 over 500 of L, the limit, which is equal to 1. What is that first term? Okay, well, what I did here is I made a comparison. I took the limit, and then I subtracted the term here. So let's just use the nth term, and we want to know where that's less than or equal to 1 over 500. Okay. So that's exactly what we accomplished here. 1, subtracting the term, we're just going to use the nth term, because then we can find out, once we know what n is, we'll know the first term. And where is that less than or equal to 1 over 500? Okay. Alright, well, let's subtract this over. Okay. We'll subtract that over and add this one over. So 1 minus 1 over 500, where is that less than or equal to n over n plus 1? Well, 1 minus 1 over 500 is 499 over 500, less than or equal to n over n plus 1. And now we can just solve this. We multiply by n plus 1 on both sides. Okay, then these will cancel. Get less than or equal to n. And if we distribute this through, we get 499 over 500. N plus 499 over 500. Okay. Now we've got our n's on the same side. we need to get our n's on the same side, so let's move that over here. So we have 499 over 500. This will be less than or equal to 500 minus 499 is 1 over 500n. Okay. And since these two are the same, we could multiply it out, or we can just see that 499 n has to be greater than or equal to 499. So when n is this number, we'll be within the limit. Now we have to figure out what term that is. That's a of 499. Remember, that's n, 499 over n plus 1, which is 500. So this is the first term that is in 1 over 500 of L. Okay. So let's see what that looks like here in the sequence. So the sequence now, 1/2, 2/3, 3/4, 4/5, etc., 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 etc. Eventually we get to 498 over 499, then we get to 499 over 500, the next would be 500 over 501, etc., etc., etc. Now this is approximately 0.997945. This one is 0.998. This one's 0.998003, etc., etc. Okay, these are approximations. And remember, we were looking to be in 1 over 500, which is 0.002. So where are the terms in the sequence? Where are we away from it? From here forward. All terms are within 1 over 500, which is equal to 0.002 of the limit L. So there was nothing special about this L that we picked, or the limit. There was something special about the limit, but not this number that we picked. All right, so we could repeat this process for 1 over 500, for 1 over 1,000. It doesn't matter. The important thing is that this will always, how close we want to get to the limit, we will always be able to get as close as we want to that limit. All right, so now I hope this helps you understand this next definition that's coming. Remember, there was nothing special about 1 over 500. I could make that number even smaller, and I could get even closer to this limit. Okay? A sequence a sub n has a limit. We'll call it L if we can make the terms, and remember the terms are a sub n's, as close to that limit as we want by taking n, so whatever n we pick, to be what we say sufficiently large. Alright, so here in this case, what I had to do is, if I wanted to be within, okay, so as close as I wanted to be was within 1 over 500. So what I had to do is I had to take n, okay, sufficiently large, and a sufficiently large n that would do that was 499. Okay. So if I'd wanted to get even closer, say 1 over 1,000, we would have to go out even further and to find what n that would be. Okay. Which brings us to, this is a continuation of this next In other words, if for every, now however close I want to get, let's call that epsilon. Okay, epsilons look like this. So for however close I want to get, epsilon, as long as it's greater than 0, we don't deal with negative epsilons. There is a corresponding integer. Okay, so let's call it capital N, such that if, okay, now n's, these are the numbers in the sequence, right? If n gets larger than the sufficiently large n, then we can say the absolute value of the function, the sequence, which is a function minus the limit, will be less than this epsilon. So another thing that we're saying is that the terms beyond a sub n, okay, so this is that capital N, where this n is sufficiently large. Okay, so in our first example, that's a sub 499. When we get beyond that term, the terms beyond that will be within epsilon, whatever epsilon we choose, 1 over 500, 1 over 1,000, doesn't matter, of L, our limit. Okay. So graphically, let's try and see what we just did from the previous example. So in the previous example, we said that epsilon was equal to 1 over 500, and for us to accomplish this, we needed n to be sufficiently large at 499. So what's happening is, okay, here's all our natural numbers. We have 1, 2, 3, etc. Okay. Here's the limit that we're looking for, or that we know. So in our last example, it was 1. Okay. Now I can go some distance above this to L plus epsilon. Okay, so there's a distance epsilon here, and I want to go below it as well. So this would have to be L minus epsilon, so whatever this, okay, so in our case, our limit was 1, so this is 1 plus 1 over 500, and this is 1 minus 1 over 500, and here's 1. Okay. Let me just extend these out so we can see what's happening here. So we asked, here's our limit, and we want it to be within, where will these function values be within here? So what's happening graphically with our function is that the sequence, we're plotting it, it's coming up, it's coming down, it's coming over, it's coming up. But at some point in time, it starts to stay within the bounds of these two lines. Okay? We don't know how long it's going to take, but eventually, as n increases, it will stay in between these two lines. And with that point where that happens, that is your sufficiently large n. Okay, so from here forward, all of the terms fall within these two lines. Okay. Okay, so that is some really strong basics of sequences. Now, we'd also like to be able to do some algebra with them, and so we need to know how to add and subtract, and etc., etc. Okay, so let's say we have two sequences, a sub n. Okay, so remember when we put these out, that'll be the first term, the second term, the third term, etc., etc., etc. And if we have another sequence, we'll call it b sub n. Okay. So its terms are going to be B1, B2, B3, etc., etc., etc. Okay, so this is what. So what do we want to do with them? Well, let's say we want to add. Okay, we can form a new sequence. That's fine. We could find the sequence that's formed when we take the sequence AN and BN and add them together. Well, the way you add two sequences is you just add term by term. So the first term in our new sequence is A1, B1. Then the second is A2 plus B2, and A3 plus B3, etc., etc., etc. Okay? So you're just going to add term by term. Okay? We can subtract them. Okay? So this would be where we take AN minus BN, and we'll do the same thing, except now we're subtracting. It'll be A1 minus B1. This is the first term of the new sequence. Then A2 minus B2. This is the second term of the new sequence. A3 minus B3, etc., etc., etc. Okay. We could multiply them. A and Bn, and we still just do this term by term. So that's A1 B1, A2 B2, okay, second term, A3 B3, etc., etc., etc. We can divide them. So AN divided by BN, and again it's just term by term dividing A1 B1, A2 B2, A3 B3, okay, etc., etc., etc. Of course, we have to watch out where about divisions by 0. So if we're going to do this, we have to remember that B sub n cannot equal 0 for any n. Right, so if out here I have a 0 but nothing else is zeros, I still can't find this this division sequence. Okay, so let's try this out. Let's see if we can do all of this. Alright, let's say, for example, then, that our sequence AN, remember I could write it like this, is defined as 1 over n, and Bn, if I write it like this, means I'm defining it to be just the number n. So let's find AN minus Bn. Well, if it helps, remember we're going to just take A1 minus B1, and then A2 minus B2, and then A3 minus B3, etc., etc., etc. So, well, what is that? Okay, well, we can do this. A1 is 1 over 1, which is just 1, and then I have to subtract off B1, which is just 1. Okay. Now, A2 is 1/2, and I'm going to subtract off B2, which is just 2. A3 is 1/3 minus 3. A4 is 1/4, and B4 is minus 4. Okay, and it would keep going. So the first few terms of this, our new sequence is going to be 0, minus 3 halves, minus 8/3, minus 15/4, etc., etc., etc. Okay, so, but that's just the first few terms. What if I wanted to know what generates this? That is, if I wanted to just pick the nth term of this sequence, what would we have to do? Okay, so this is a new sequence, C sub, let's call it C sub n. Okay, now we know C sub n is equal to A sub n minus B sub n. Okay, that's how we got it. So if we want to find it specifically, we could take 1 over n and subtract n, which, if we get a common denominator, C sub n is generated by 1 minus n squared over n. Okay, So this generates this. And now I could find any term in this sequence. Okay, so now let's talk about limit laws, all right? So we can add and subtract sequences. And now that we've done that, the limits will also follow their own rules. Okay. All right. So this is a theorem, and this is something we're going to need to know. Okay. So our limit laws here for sequences. And we'll need these when we're going to start determining. So here's our theorem. So that means it's something that's already been proven for us, and we can just use it. We don't have to reprove it. So if the limit of n, as n goes to infinity, of a sequence a sub n, let's say that exists, we'll call it a. Right? And we have a limit, a convergent sequence, so let's call it b sub n. And we'll say that limit exists, so we'll call it b. Let's say these two things happen, and we're going to let c be a constant. Okay. Then, once we have these two things, so I've got a constant, two sequences that are convergent, each with their own limit. Right? Then we can say these things. Then, if you wanted to look at the limit as n goes to infinity of now the sequence an plus bn, right? I don't have to individually add each of these two terms and then look again at the limit of the sequence. What I can do is I can just say, well, that's the limit of a plus b. Okay. And the same will hold true for the subtraction. Okay, so I'm taking the limit of an minus bn. Again, I don't have to go through and do every single term. I just know then that it's the limit of a minus the limit of bn. And it holds true for the multiplication as well. The limit as n goes to infinity of, if I was to multiply all of them, then all I would have to do if I'm looking for the limit is multiply the limits. For the division, it will also hold, provided the division can be done. That'll just be a divided by b. Okay. But now we actually have to add. Remember, b sub n cannot equal 0 for all n. And now we have to worry then that the limit here, b, also cannot equal 0. Okay, so division by 0 is no problem. And there's also one about a constant. So let's just say I wanted to take the limit as n goes to infinity of a constant times a sub n. So I'm just multiplying each individual term of an by this constant c. I don't have to refigure it out, but for the limit then it'll just be the constant times the limit of the sequence. Okay, so these are five that we'll need to know. Also another helpful theorem for us that we've actually used earlier in the course when we were dealing with rational functions, something very similar. So let's say that we have the limit as n goes to infinity of 1 over n. Okay. So remember, we were using this in rationals, and we said, well, what happens if the denominator gets very, very, very large? And we said what happens then is that the limit goes to 0. Okay, so let's do some examples and seeing if we can't determine limits. Okay, let's find the limits. Okay, so let's look at this. The limit as n goes to infinity of 3 over n. What is that limit? Okay. Well, we have to use our limit laws. So one thing that we can notice then, this is the same thing as the limit as n goes to infinity of 3 times 1 over n. Okay? If I multiply these back out, I'd get 3 over n. Well, now this is just a constant, and this is 1 over n. I could split this up. I could say, well, that's just the limit as n goes to infinity of 3 times the limit as n goes to infinity of 1 over n. And now I know from the above example that this is 0, and the limit of n goes to infinity of 3 is just 3, because there is no n. It is constant. So in the end, this limit is still 0. What about the limit as n goes to infinity of 1 over n squared? What's this limit? Well, let's do some rewriting. This is the limit as n goes to infinity of 1 over n times 1 over n. And now I can split these up. That's just the limit as n goes to infinity of 1 over n times the limit as n goes to infinity of 1 over n. And now from the theorem of above, the limit as n goes to infinity of 1 over n is 0. This is also 0. 0 times 0 is 0. So now in general, this will be true. The limit as n goes to infinity of 1 over n to any power is going to be equal to 0. Okay, so 1 over n to any power will be 0. Okay, let's try a more difficult one. Alright, so we've got a sequence, and let's let it be generated by a sub n that is equal to 3n squared plus 2n plus 4 over n squared plus 1. Okay, so remember when we were doing this with rational functions, when we looked at the limit, we had infinity over infinity. So one trick that we did is that we took the highest power in the denominator, okay, and we were going to divide everything by that power. That's what we're going to do. So I should write this out so we can see it. Okay, so the limit as n goes to infinity of 3n squared plus 2n plus 4 over n squared plus 1. This is what we're trying to find. The way we're going to do it, now I haven't taken the limit, so I'm going to rewrite this. The limit as n goes to infinity of, now 3 over n squared was just 3. 2n divided by n squared is 2 over n, plus 4 over n squared is equal to 1 plus 1 over n squared. Okay, so that was just by rewriting this step. Okay, now that we've done that, we can go term by term by term and think about what the limit is. So this is equal to the limit as n goes to infinity of 3 plus the limit as n goes to infinity of 2 over n plus the limit as n goes to infinity of 4 over n squared divided by the limit as n goes to infinity of 1 plus the limit as n goes to infinity 1 over n squared. Okay, so, well, now what? What are we going to do? Well, now here, the limit as n goes to infinity of 3, there is no n. Okay, so this has to just stay at 3. And similarly down here, there is no n. The limit as n goes to infinity of 1 is just 1. Now here, this is the same thing as 2 times 1 over n, but 1 over n, the limit of that just goes to 0, and 2 times 0 is just 0. We know 1 over n squared, its limit is also 0. And this is just 4 times 1 over n squared, so 4 times the limit, which is 0, that also goes to 0. So in the end, this limit is 3 plus 0 plus 0 over 1 plus 0, which is 3 divided by 1, which is just 3. Okay, so that's a lot, and that should get you through your homework. Send me an email if you have a question.